it is what it is. Let us begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for these students. We thank you that your salvation is by grace and not by our works, and that it's because you are holy, not because of anything that we've done, that we are able to be saved, Lord. And I just ask you to bless this class today, Lord. In your name I pray. Amen. Okay, so let's talk about a little theorem. Well, before I even get to the theorem, I need to talk just a bit about polynomials of operators. Okay, so this is just a neat bit of algebra. So if we have f of x is equal to, say, c0 plus c1x plus c2x squared plus plus cn x to the n, all right? So if this is a polynomial over some field f, so that means that the coefficients c0, c1, c2, and so forth and so on are in the field, then definition f of t, all right, is a corresponding polynomial, not polynomial, but operator, is c0 plus c1t plus c2t squared plus ... plus cn t to the n. So given any polynomial, we can construct a corresponding polynomial operator by just replacing x with the operator. And what does t squared mean here? By the way, we'd say that this is an element of ft. So this is polynomials in the operator. So this is definition. Let me just show you how that works. So here, this is for t, a linear transformation from v to v is my primary interest. So I want to start class by proving a little result that we're kind of using all over the place theoretically. I think it's a nice little thing to start with. And I knew you guys would be coming in late, so for reasons outside your control, I understand that. Okay, so endomorphism. This is how we form f of t. What does this expression f of t mean? How does that work? ft, if we let that act on a vector v from the vector space v, how does that work? Well, that's equal to c0 v plus c1 t of v, all right, plus c2 t of v, and so forth. Cn times the nth power of t acting on v. Where tnv means that's actually t of 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 v, right? You let t act on v n-fold times, that's t to the n on v. So this is, this is how f of t acts on v. And what's the output again? This thing I just wrote down, where is that? Is it a number? Is it a vector? If t is a linear transformation from v to v, t of v is again a vector. T of v is a vector. This is a linear combination of vectors in a vector space. This is again a vector, all right? And in fact, you can prove, here's a little theorem for you. If t is linear transformation from v to v, then f of t is a linear transformation from v to v for any f of x in any polynomial. So a polynomial of a linear operator is again a linear operator because the sum and composition of linear transformations is again a linear transformation. All right? Yeah.
Could this be considered an invariant subspace?
Invariant subspaces. That's what I wanted to talk about. So here's a theorem. The invariant subspace that I have in mind is the kernel of f of t is an invariant subspace of v for any f of x in any polynomial and any t, which is, you know, a linear transformation from v to v. Okay. So yeah, there is a invariant subspace attached to this idea, the kernel of any polynomial, and so let's prove it. So what's involved in the proof here? What does it mean for and to be more clear, what kind of invariant subspace am I talking about? Like invariance of a subspace is with respect to a linear transformation. So I specifically mean a T invariant subspace. So let's say x be an element of the kernel of f of t. All right. So that means what? F of t acting on x is equal to 0, right? Then consider t of f of t acting on x. Now here's the neat thing. Here's the neat thing, guys. This can be rewritten as t times f of t acting on x. So like the way polynomial operators work is the algebra that they satisfy is just like regular algebra. I'll write this down systematically after the proof. My bad, I should wrote it before, but Zach's question tempted me to skip ahead, so it's good. But the thing is, these flippity-floppity, these commute, right? If you have x times f of x, it's equal to f of x times x, right? Can you multiply x before or after a polynomial? It commutes, right? It's a commutative thing, so that's also true for this. So what are you looking at? Oh, I think I've what am I trying to show? I would like to show that, sorry guys, my goal is to show that t of x is an element of the kernel of f of t, right? So what does it take to show that t of x is again in the kernel of f of t? What do I need to look at? Yeah, I should look at f of t acting on t of x. I had my starting point was the reverse of what I should have been doing in my previous. All right, the computation I just mentioned is the one we have to do, but logically we should start with that. because we're trying to show that t of x is in the kernel. All right, so I do that. This is equal to f of t times t acting on x, but by properties of polynomials, we can commute t times f of t like that. And then we're looking at t times f of t acting. What is f of t acting on x, though? By assumption, it's 0, right? So we're looking at t of 0, which is 0 again. So therefore, t of x is an element of the kernel of f of t, right? Which, in summary, shows us that t of the kernel of f of t is a subset of the kernel. I can't make up my mind whether kernel is uppercase or lowercase. You'll forgive me. And that's what, remember, this is what's required to show invariant subspace. We used w before, right? Like t of w is supposed to be a subset of w. That proves that w is an invariant, is a t invariant subspace, right? This was the definition of t invariant subspace. So yeah, the kernel of any polynomial in T forms an invariant subspace. Okay? So applications of this theorem, right? You know, E lambda, which is the kernel of T minus lambda. That's an invariant subspace for a given endomorphism T. And if, suppose the characteristic polynomial of T of x, which would be the determinant of, in my notation, t minus x. All right, and so suppose that works out to minus 1 to the n, x minus lambda, 1 to the m1, and then whatever, I don't care whatever else here, g of x where g of lambda 1 is not equal to 0. What am I trying to say here? I'm trying to say lambda 1 is an eigenvalue of t, all right? It's an eigenvalue of t with algebraic multiplicity m1. All right, in this case, it's interesting to define the generalized eigenspace, all right, the generalized eigenspace, k lambda 1, as being the kernel of, well, still t minus lambda 1. If I recall correctly. Let me double check on that. It's been a bad day today for me, guys. Don't even get me started on what I did in Calculus 2 today. I said, don't get me started. It's just, I just made things more complicated than they actually are, is the main thing. Okay, so yeah, I messed it up. So, well, I think this is right, actually. No, it's not. It's not. I need think M1, oh curses, how to say this. This is not quite right. I mean, it's not right. So what we're looking for here is x in V such that t minus lambda 1 to some power p acting on x equals to 0. All right. So of course, E lambda 1 is automatically a subset of K lambda 1, right? Because in particular, the generalized eigenspace for lambda 1 includes eigenvectors with eigenvalue 1, but it could also include so-called generalized eigenvectors of order 2 or 3 or so forth, all right? What I'm struggling with is I'm pretty sure that K lambda 1 is the kernel of a given polynomial, all right? I think it is. And I just can't quite convince myself to put something there, all right? Let me make a definition for you guys. If t minus lambda acting on x is equal to the power p is equal to 0, yet t minus lambda to the p minus 1 acting on x is not equal to 0 for some non-zero x, then x is a generalized eigenvector of order p for t, and here we're assuming t goes from what? Linear transformation from V to V, you know. V is a vector space. Again, I'm assuming t is a linear transformation from V to V over a field F, and the lambda is a scalar in that field. All right? So this is a generalized eigenvector of order p, right? Let me just focus our attention on a specific numerical example to try to unwrap these ideas. So if I have A equals to, let's say, I'll write it this way, the, good grief, the Jordan 3 block of 2 direct sum with the Jordan 2 block of 1 direct sum with the Jordan 3 block of 2 again, all right? So this is a what by what matrix? So it's got 2, 2, 2. All right, 1's on the super diagonal. That's the 3 by 3 Jordan 2 block, all right? Point number 1. Then J2, that's a 2 by 2 block with eigenvalues 1 on the diagonal there. And then oh, I'm sorry, I didn't want to put a 3 here. I wanted to put if it's okay with you guys, I'm going to put a 1 here, okay? Notice I'm erasing this 3 and making it a 1 for the sake of just making it a little bit different. So a Jordan 1 block down here, that would just put a 2. All right, so everything else is 0. So you got like 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Oops, wait a minute. There's only one column there. Don't let me get carried away with my zeros. Is that enough zeros? So you can see why we don't write those sometimes. It doesn't really add a lot of information, and it's actually kind of distracting to write the zeros, isn't it? But I write them so that this doesn't seem fuzzy to you. That is literally the matrix we're looking at. In this case, let's see here. A minus 2i is what? Right, that's A minus 2i. And what's A minus I while we're at it? So you guys tell me, what is the eigenspace with lambda equal to 2? The span of what? For this matrix, what are the eigenvectors? I mean, I guess I can write something before I write that down. It's the null space, right, of A minus 2i. Here's A minus 2i. Well, it looks like E1's a good choice, right? Because E1 times A minus 2i is 0, because that's the first column. Well, E2 is not in there, E3 is not in there, E4 times A minus 2i is not in there. See, any of the standard bases times that matrix gives you a non-zero column in the matrix, right? I mean, remember our theorem, if we take the jth column, jth standard jth standard vector, jth standard basis vector times a matrix, it picks out the jth column of the matrix, right? So using that, the last column, so what do you say, E6, all right. So the dimension of the lambda equals to 2 eigenspace is 2, right? Which is less than the algebraic multiplicity, right? What's the algebraic multiplicity of 2 here? What's the characteristic polynomial for this example? You're like, that's a complicated question because that's the determinant of A minus x times the identity, right? But here I can tell you what that is. That's minus 1 to the 6 times x minus 2 to the 4th power times, x minus 1 squared. All I'm doing is you can read the eigenvalues off the diagonal because this is an upper triangular matrix. This is a theorem. If your matrix is an upper triangular form, then the eigenvalues, whatever's on the diagonal, are the eigenvalues. Or you could calculate the determinant directly and get this. Anyway, that's it. So the algebraic multiplicity of lambda equals to 2 is what? It's 4, right? The algebraic multiplicity of 2 is 4. This matrix is not diagonalizable because eigenvalue 2, the algebraic multiplicity is not equal to the geometric multiplicity, among other things. All right. What else can I say here? Well, E lambda equal to 1, which let me just call that E2 versus E1, all right? What's E1 equal to? That's the null space of A minus I in this case, which is, by the way, the span of, well, E4, right? E4 is the only, well, it is a basis for the eigenspace. So the geometric multiplicity of 1 is just 1. What's the algebraic multiplicity? It's less than 2, which is the algebraic multiplicity, right? I know that the algebraic multiplicity is 2 because I look up here, the characteristic polynomial has an x minus 1 in it. What are the generalized eigenspaces then? Certainly, by the way, it's not the case. You notice that, if we take E1, direct sum E2, it's not equal to R6, is it? Because E1 is two-dimensional. E1 is one-dimensional. E2 is two-dimensional. So the direct sum of the eigenspace is just three-dimensional. That does not give me R6. Okay, so what's K1? Dang it, I should have started this over there. Oh well. All right, see if I can fit some things in here. So notice that let's see here, A times E3 is equal to what? It's equal to E2 plus 2E3, right? So therefore, A minus 2I times E3 is equal to E2, all right? Also notice that A times E2 is equal to E1 plus 2E2. And I'm just looking at the second column and the third column of the matrix, right? And so if you look at that, that says that A minus 2I E2 is equal to E1. And of course, we already noticed that A minus 2I E1 was equal to what? It was equal to 0, right? E1's an eigenvector with eigenvalue 2. So the bigger idea here is I can basically start with E3. I can multiply by A minus 2I. That gives me E2. And I can multiply by A minus 2I again, and that gives me E1. All right, what else can I want to say more. In fact, E2 and E3 are generalized eigenvectors, okay? I guess I'll write, I do have another board over here, don't I? So notice that A minus 2I squared times E2 is what? Do you see why that is? What did I do there? I took one of the A minus 2i's, let it act on E2. That gave me E1. We've noticed that already, right? But what's a minus 2I times E1? It's 0, right? So notice then that E2 is generalized eigenvector of order 2 for lambda equals to 2, right? Because when we take the square of a minus 2I acting on E2, we get 0. But when we take 1 power less, it's non-zero. Likewise, a minus 2I cubed, cubed acting on E3 is a minus 2I times, well, a minus 2I squared times a minus 2I E3, right? But this is E2, right? And so what we're looking at is a minus 2I squared acting on E2, which we just worked out is 0. But what else? There's something else I should mention. What's a minus 2I squared acting on E3? Let's see, if I just take one of them, I get E2, right? And that's what? That's E1, right? Which, of course, is not equal to 0. So therefore, E3 is generalized eigenvector of order what? 3 for eigenvalue 2 with respect to the matrix A. So what I'm trying to get at here, this generalized eigenspace, K lambda equals to 2, it is the span of everything that's attached to Jordan blocks with eigenvalue 2. It's E1, it's E2, it's E3, you know? And also E6. This is for this example, this is what the, I'm trying to think of how I can explain what that is. I want to say it's the kernel of something. It's the kernel of what, though? It's not the kernel of just a minus 2I, right? That's not quite it. I think it's the kernel of a minus 2I squared. In order to see that, I probably should write down what is a minus 2I squared. Can you guys tell me what is a minus 2I squared? Square that, what do you get? You get this. Oh, by the way, if you're squaring a block diagonal matrix, you can just square the blocks. Good to know, huh? Well, it's helpful for this calculation especially. I'm just squaring the blocks individually. What's the kernel of that matrix? Looks like I'm wrong, right? What should I have put? I should put a 3 here, right? If I put a 3, then I think we'll get everything that I wanted. The cube is what? You've got this 3 by 3 thing of zeros up here, This is still non-zero. I don't know. I think it's -3, isn't it? I don't know. Do I get... Oh, it is a -1. Listen, I don't really care what goes here. Stuff. Okay? I know that there's a 0 here, but there's stuff in here. Whatever it is, it's there, but it's non-zero, by the way. I'm taking entirely too much time for this example. It's starting to wear on me. Stupid. Anyway, the point is, this does have E1, E2, E3, and E6 as its kernel. So, right. So it's hard for me to, like, the generalized lambda eigenspace, it's going to be the kernel. It's not just the kernel of the algebraic multiplicity, right? So the algebraic multiplicity of 2 here was 4, but I actually needed to use 3. The kernel of a minus 2i to the 3rd power is what I needed to generate the generalized eigenspace of order 2. I can tell you in words what it's going to be. If you find the Jordan form of the matrix, the generalized eigenspace, it's like it's the, you look for the largest block that has that eigenvalue, and it's that power that you need. All right, I'm being vague. I'm sorry. But the larger point is that that's an invariant subspace, like the k lambda equals to 2 is an invariant subspace because it's the kernel of that polynomial. Oh, by the way, we can also do a polynomial of a matrix. The same, I did it for an operator, but you can just as well define polynomial of a matrix. All right? So that's k lambda equal to 2, and this one, if we look at a minus, what happens when we square this? If we square this, right? This, I don't care, it's something. And this is still 1, and this is 0. So like the kernel of a minus I squared is the span of 1, 2, 3, E4, and E5. And while it's not the case that E1 direct sum E2 is all of R6, it is the case, my thing I was trying to get to, and I need board over here. I could just, whatever I write that way, it's got to be good because it's going to be up there forever. This doesn't quite raise to that level. I wouldn't trust myself to write anything of lasting value today. So, dang it. Decisions. This is the worst. This is what I was talking about. This is exactly what happened in Calc 2 this morning. Okay, so my point was that R6 is in fact K1 direct sum K2. And this can always be done if your eigenvalues are in the field. The direct sum of the generalized eigenspaces always forms the whole space. And you can find a basis of generalized eigenvectors which puts the matrix or the transformation into Jordan form. Let me try to redeem this train wreck of a lecture with cookies. Ha! Ah! Very funny. You can do it. You can do it. You can do it. All right, very good. It's not. It's from real life. It's from the Olympics when that monstrous coach made that poor little girl break her ankle for the sake of sports fans' amusement. Well, she was already limping, and then they made her do that final vault, and then she like broke her leg.
Oh yeah, that's right.
And he's on the sideline. You can do it. You can do it. Sorry. That is the context in when I say you can do it should be understood. Every email I send to you, every announcement I send, I say hi everybody. That should be understood. That's the hi everybody from The Simpsons. Like there's a character who goes, hi everybody. That's how that should be read. You've been reading it wrong all these years or weeks. Listen. So calculating a Jordan basis, and so this thing I showed you over here, this makes E1, E2, and E3 form a chain of generalized eigenvectors of length 3 with eigenvalue 2. All right? Each chain of generalized eigenvectors will correspond to a Jordan block in the Jordan form of your matrix or transformation. So if you're given a matrix which is already in Jordan form, it's very easy to find a Jordan basis. It's just the standard basis properly understood, which is what I went through here, taking entirely too much time and still leaving you confused somehow. How did I do that? I don't know. It's my gift. But for a more interesting matrix, like this one, to calculate the Jordan form, you have to find a Jordan basis. How do you do that? Well, you calculate the characteristic equation. Steps not shown, right? That's a 4x4, factoring a 4x4 matrix. Like that's a significant page-long calculation I didn't show you the details of in this example. But it is x minus 2 squared times x minus 4 squared for this, right? And then I figured out that there are eigenvectors, 2, 1, 0, 2, 0, 1, 2, 0, 0, 1, 1, 1, 0. These are eigenvectors all with eigenvalue. Well, the upper two with eigenvalue 2, the last one with eigenvalue 4. At this point, I already know that the algebraic multiplicity matches the geometric multiplicity for eigenvalue 2. Because I have two linearly independent eigenvectors, those are both in my my eigenspace with eigenvalue 2. And look up here, I can see that the algebraic multiplicity of 2 is 2, so when that's it. We don't need to look for any generalized eigenvectors with eigenvalue 2 in this problem. On the other hand, for eigenvalue 4, I found just one eigenvector, right? I know by the general theory that there exists an eigenbasis for this problem because the eigenvalues were 2 and 4. They're both in the field, so there exists a Jordan basis. That Jordan basis is going to have 3 eigenvectors, apparently, these guys. And I need to find the next one. Actually, I have it right here. A minus 4i times this vector gives me that vector. So that means that this is a generalized eigenvector of order 2. Because if I took the square of a minus 4i acting on it, I'd get 0, just like we had. I erased it. So yeah, the one thing I was going to reference, it's erased, of course. Great. Anyway, this is a Jordan basis because what I have arranged here is, well, these are the eigenvectors with eigenvalue 2. So when I similarity transform by that basis, I get 2, 2, 0, 0, like there. And the other one gives me a Jordan block with eigenvalue 4, right? Wherever you don't have enough eigenvectors, there will be blocks, right? But there's always one eigenvector for every block as well. There's always one eigenvector for each block. Okay? Here's another example. So for the in-class test, just try to be transparent with you guys. I don't usually ask, there might be one problem on the test that actually has you trying to calculate like generalized eigenvectors, but it's kind of a pain for anything big. It's much easier for me to ask a conceptual question, which is like essentially something like akin to example 1, where I give you a matrix in Jordan form already and ask you to interpret, to find the Jordan basis and explain, identify the chains, the eigenvalues, the geometric multiplicity, the algebraic multiplicity for each eigenvalue. There's something called a minimal polynomial. What's a minimal polynomial? It's the smallest polynomial you can get. Well, the minimal polynomial for t. Is lowest degree monic m of x in f of x such that m of t equals to 0. Likewise, if you have a matrix, the minimal polynomial of a matrix, it's the smallest. What's a monic polynomial? For my example 1, the minimal polynomial for a of x is equal to, I can tell you what it's equal to. It's equal to, oh man, curses, x minus 1 squared times x minus 2 cubed. You can compare that to the characteristic polynomial for a, which was x minus 1 squared times x minus 2 to the 4th power for this one. How do I know that's the minimal polynomial for a? Because I studied this for a long, long time. No, it's because of the matrices on the board. So if you take a minus 2i cubed and you multiply it by a minus I squared, notice that the 0 blocks line up with the non-zero blocks and vice versa. So you always have a 0 in each block when you're multiplying. That 3 by 3 0 hits this 3 by 3 non-zero. That middle non-zero hits this middle 0. And this 1 hits that 0. So when you multiply these two things together, you got 0. And anything smaller doesn't happen. There's always something that doesn't zero out below that. Let me tell you a theorem which is super, super helpful, which I will not prove, but is very useful for problems. This is the so-called Cayley-Hamilton Theorem. It says that the characteristic polynomial of a evaluated at a is 0. Same for an operator. If you take an operator or a matrix and generate the characteristic polynomial, right, that gives you a polynomial. If you take that polynomial and you plug the matrix into it or plug the operator into it, it works out to 0. So one of the things this means is that the minimal polynomial will always have to divide the characteristic polynomial. You're like, what do you mean, divide? I mean that they share the same factors, and the minimal polynomial will have the same factors as the characteristic polynomial, but possibly lower order, right? Like it just straight up shares the x minus 1 squared, but as you can see, we didn't need the 4th power. Right? If you plug a into the characteristic here, you'll get 0. This example, I'll just say in a word since I started super late. This is an example of a linear transformation on P2. I work out the I work out that the eigenvalue here is -1 with algebraic multiplicity 3, and it turns out that the matrix plus I squared is non-zero. That means that this is actually going to have, there's only one eigenvector here, is the large. So this is an example with algebraic multiplicity 3, geometric multiplicity 1. And so that means we have one 3 chain. And the calculation here, I work out that, come on. This and this are a generalized, a chain of generalized eigenvectors. And this is it's a Jordan, it's J3 of -1 there, so it's in Jordan form. Can't be diagonalized, and that's it. All right, anyway, enough. Next time I will start with the complexification and so forth. I'm sorry. Why should I be sorry? I'm not the one that's late today.